This conference will now be recorded.
Very good evening, students. Today we'll be discussing an important topic, that is Earth magnetism. So actually Earth has its magnetism, and that is felt everywhere on its surface, and the magnitude of the Earth magnetic field is of the order of 10 to the power minus 5 Tesla. 10 to the power minus 5 Tesla. The branch which deals with the study of Earth's magnetism is called geomagnetism or the terrestrial magnetism. Okay, so this is fine, but what makes Earth a magnet, or what is the origin of Earth's magnetism? So there are many theories, but the most authentic theory or most authentic explanation of the origin of Earth's magnetism is the convective motion of molten metallic fluid, that is molten iron or nickel. So due to convective motion of this metallic fluid at the outer core of the Earth, an electric current is produced, and that electric current actually produces magnetic field. As you know, electric current produces a magnetic field around it. Okay, produce magnetic field around it. This will be this way. Sorry, magnetic field around it. Similarly, here it is said that, see, in the core there are nickel and iron, and at the core there is a huge temperature, and there everything is in the molten state. So at the outer core, this molten iron and nickel are there. So these are acting as fluid over there. So molten metallic fluid. So molten iron and nickel are in the form of metallic fluid. And as you know, because of Earth's motion, there is a convective motion of this molten iron and nickel. As you know, iron and nickel, see, iron has free electrons, like to provide magnetism. Nickel also has free electron to provide magnetism. So as electrons or charged particle moves, they produces a current, right? So that convective motion produces an electric current, and that electric current produces in turn a magnetism. That this effect is actually called dynamo effect. This effect is called dynamo effect. Okay, so iron, nickel, they are actually good magnetic materials. We'll be discussing. Actually, see, the origin of magnetism is unpaired electron. Origin of, okay, unpaired electron is actual origin of magnetism in any matter, any material. Okay, what is that? Unpaired electron. Unpaired electron is the origin of magnetism in matter. Oh, sorry. Origin of magnetism in matter. So Earth behaves. So we can see Earth behaves as a magnet. So how to visualize that Earth's magnetism? To visualize Earth's magnetism, we can actually hypothetically think that there is a huge bar magnet through the Earth, okay, through the Earth, through the core of the Earth, and the poles of that bar magnet is situated near to the geomagnetic poles, sorry, geographic poles. Okay, so to visualize the Earth's magnetism or Earth magnetism, we can consider that there is a huge bar magnet inside the core of the Earth, whose poles are situated near to the geographic poles. Okay, geographic poles. Okay, obviously here we can see that the south pole of the bar magnet is near to the geomagnetic, sorry, geographic north pole, and the actually the north pole is situated near the geographic south pole. So this can be verified with the magnetic field lines. Okay, with the drawing of magnetic field lines. See, the magnetic field lines generally comes out of north pole of the bar magnet, as you know, and that goes all the way. And see, if this is south, this is north pole, so magnetic field lines will go like this, and it will go inside the magnet also. Okay, this will make a closed loop. Okay, this is how it is. So the field lines will be coming out, okay, or emerging from north pole. So Earth's magnetic field, see, the field lines due to Earth's magnetic field is also seen to be coming out from the south pole, geographic south pole. So that's why the magnetic north pole is situated near to the south pole, and south pole is magnetic south pole of the Earth is situated near to the geographic north pole. So this is for visualization. We can think that there is a bar magnet inside the Earth, core of the Earth. Okay, so one thing we could see, so it is seen that the magnetic north pole and the geographic north pole, or the axis of the Earth, geographic Earth, sorry, geographic axis of the Earth and magnetic axis of the Earth, they are not coinciding. Okay, that means magnetic north pole and geographic north pole, they do not coincide exactly. Okay, there is an angle between the geographic axis. So what is geographic axis actually? Axis. So this is the straight line. This is a straight line joining geographic north and south poles. South poles. Okay, and it is called axis of rotation also. Axis of rotation of the Earth. Axis of rotation of the Earth. Okay, this rotation actually is the rotation of the earth about its own axis. So this axis is actually geographic axis. As you know, this is the geographic axis. Okay, this line is the geographic axis. Okay, so there is always an angle between geographic axis and magnetic axis. So magnetic, if this is the bar magnet, so this is north pole, this is south pole. Here obviously we are just writing north pole this one, but this is not north pole exactly. You will see this field lines are entering into the earth at this particular position. So this should be south pole, but conventionally to understand the earth magnetism, sometime north pole is denoted near the north pole itself, geographic north pole itself, and south pole is denoted near the geographic south pole itself. Okay, sometime it is the notation. But you look these field lines. These field lines are emerging out from the south pole, which is not possible. So that's why this south, actually this particular pole is called north seeking. This is actually south seeking pole. This is called south seeking pole. That's why it is given. That means this must be the north pole of the earth magnet. Okay, okay, earth magnet. Because if you just bring a bar magnet, the south pole will be attracted towards this. So this is called actually south seeking pole. Not exactly south magnetic pole, south seeking pole. And this is obviously it is called north seeking pole. Okay. All right. So here we will be learning few more terms. We have already learned what is geographic axis. Similarly, there will be geomagnetic axis also. Magnetic axis. So what is this geomagnetic axis? It is the straight line joining the geomagnetic north and south poles. Okay, I'm not writing here, similar to this definition. Now what is this magnetic equator and what is this geographic equator? See, geographic equator, it is the great circle. If you draw the great circle which is perpendicular to the geographic axis, see, this is the great circle which is perpendicular to this great circle is drawn on the surface of the earth, and since earth is nearly spherical, so you will get a circle itself. So this circle is perpendicular to, or right, so perpendicular to the geographic axis. So this is called geographic equator, and this geographic equator, you know, it makes this earth into two equal hemisphere. Okay, so this is called northern hemisphere, northern so this is north hemisphere or northern hemisphere. Northern hemisphere or north hemisphere. Northern hemisphere or north hemisphere, and this is southern hemisphere or south hemisphere. Or south hemisphere. Okay, so these are actually two equal parts, and the plane which is contained by this equator, geographic equator is actually called equatorial plane. This plane is equatorial plane. Okay, equatorial plane. Okay, this equatorial plane is actually horizontal to the surface. Okay, so equatorial plane. So how much angle this makes? Equatorial plane is making an angle 90 degree with the pole. So this is the pole and this is equatorial plane. So with the pole, equatorial plane makes an angle 90 degree. Okay, or the axis, with the axis also it makes, with the rotational axis it makes 90 degree angle. All right, so similar to this geographic equator, we can imagine a magnetic equator as well, which is see the great circle. You can see this is also another great circle which is perpendicular to the geomagnetic axis. Look, this is the geomagnetic axis, and this is the great circle on the earth surface. So this is actually called magnetic equator, and this plane is called magnetic equatorial plane, geomagnetic equatorial plane. Okay, now see, there will be we'll be discussing another term that is called meridian plane. What is this meridian plane? What is meridian or magnetic meridian or geographic meridian? See, the plane contains this rotational axis or geographic axis, which is perpendicular to the magnetic equator, or we can say the plane passing through the geographic axis. Okay, geographic axis or axis of rotation of the earth is called geographic meridian. And similarly, see, magnetic meridian is the plane which is passing through. So this is the magnetic meridian plane which is passing through the magnetic axis. So this is the bar magnet and this is the axis, magnetic axis. So the plane which is passing through the magnetic axis is called magnetic meridian plane. Okay, so these are few terms we have learned: magnetic axis, then geographic axis, geomagnetic equator, geographic equator, equatorial plane, then geomagnetic meridian, geographic meridian. Those things we have learned. Now we'll discuss about the elements of Earth's magnetism. So there are actually three parameters. There are three parameters which are essential to describe the Earth's magnetic field or Earth's magnetism quantitatively. Okay. So quantitatively, if we want to determine the magnetic field at any position, I hope I have okay. Okay, I have, yes, I have actually missed few definitions before I go to this Earth magnetic element. I'll just discuss here itself. Okay, so there are excuse me, there are three essential parameters which help us to determine the Earth's magnetic field quantitatively. Excuse me. So these three parameters, essential parameters, are angle of declination, which is denoted by alpha, angle of dip or angle of inclination, which is denoted by delta, and horizontal component of Earth's magnetic field, which is denoted by BH. I'll first make you learn what are these parameters, like angle of declination, what is angle of declination, what is angle of dip, and how to measure them. And then we'll discuss what is earth, earth's horizontal component of magnetic field and how it helps us to determine the magnetic field quantitatively at any position of the earth. So first let us learn about angle of declination or magnetic declination. So as I discussed before, that magnetic geographic axis or axis of rotation of the earth and geomagnetic axis, they are not coinciding with each other. So the angle between geomagnetic meridian and geographic meridian is called the angle of declination. Okay, or magnetic declination. It is denoted by alpha, as you know. See here it is shown. So generally, if you want to know the actual direction of the geomagnetic, actually the direction that was north and south pole indicated by a magnetic needle of a compass, okay, or compass needle, is actually indicating the direction of magnetic north and south poles, okay, not the geographic north and south pole. So if you want to so if you want to determine, so first of all you have understood, so it is the angle between the magnetic axis and geographic axis or meridian. I have just told with meridian plane or meridian. This is geographic meridian, this is geomagnetic meridian. So the angle between them is this alpha, okay. So this is actually magnetic declination or angle of declination, okay. So how to determine magnetic declination? See, if we want to determine the magnetic declination, then we have to set up a compass needle or fixed the compass needle vertically, sorry, not vertically, horizontally. So you have to hold fixed at some places and pivot it in such a way that it can I'm really sorry. So it has to be pivoted in such a way that it can rotate in the horizontal plane. It can rotate in the horizontal plane like this. If you take a compass needle, then fix it at any position where you want to calculate the angle of declination. So you have to fix the compass needle in such a way that it can rotate horizontally about the axis which is passing through its pivot. And this axis is obviously, you can see, this is vertical axis, okay. Now the angle which is made by the needle with the geographic north south direction, See, you know geographic north and south directions. Okay. Now at the, you see, if you just keep just like that, the magnetic needle will actually come to its rest, or it will settle down, giving some direction north here, magnetic north, and this is magnetic south. And suppose this is the geographic north and south. Okay, this is geographic north and south. Okay, so this angle between this is actually will be, so by knowing the declination we can determine the vertical plane in which the earth's magnetic field lies. See, in India the value of alpha is very small actually. Okay, it is, see, if I say alpha equal to 0 degree 41 minute east for Delhi, east for Delhi. Okay, and it is alpha is equal to 0 degree 40, that means 48 minute west for Mumbai. Okay, this means north pole of a compass needle almost points to the direction of geographic north in case of India. So it is very small, right? 41 degree at Delhi and 58, not degree, this is 41 minute, 41 minutes, and at Mumbai it is 58 minute west. Okay, now we'll learn about angle of dip or angle of inclination. So angle of dip is the angle made by the total magnetic field of the earth with the horizontal direction of the magnetic meridian. So it will be a little bit difficult to understand without the figure. Look, this is the figure. See here, this is actually magnetic meridian. As you see, magnetic meridian means, you know, like if you have bar magnet, north and south pole, I have already shown you. So this is the magnetic axis. So the plane just passing through this. Okay, passing through this. Okay, passing through this axis, magnetic axis. So that is actually magnetic meridian plane, and geographic meridian is the same as this, like the plane which is passing through the geographic axis. So this is geographic meridian, this is magnetic meridian, and angle between them is declination. Okay, angle between them is declination. Look here, the angle between them is alpha, magnetic meridian, and this is geographic meridian. Angle between them is alpha. Now this is the horizontal direction. So this is horizontal direction of magnetic meridian, and this is vertical direction of magnetic meridian. Okay, this is vertical direction, this is horizontal direction. Okay, this is horizontal direction, this one. Okay, all right, now see the angle definition wise, the angle of dip is, or angle of inclination is the angle that the total magnetic field of the earth, see, this is suppose the total magnetic field B, which is making an angle delta with the horizontal direction of the magnetic meridian. So this is actually the angle of inclination. The total magnetic field of the earth is making an angle with the horizontal direction of the magnetic meridian. So that particular angle is delta here, which is angle of inclination. So how to determine the angle of inclination? See this figure. So to determine the magnetic inclination, angle of inclination, what you have to do? At different places you want to measure. So what you have to do? You have to fix the compass needle. See how it is fixed? In such a way that it can rotate in the vertical plane. Okay? Vertical plane in the sense, see, in the plane of magnetic meridian. Okay? So consider the needle, compass needle, which is used for measuring the angle of dip. This is called dip needle. This is dip needle. Dip needle. Sorry, I am sorry. This is dip dip needle. This is called dip needle. Dip needle. Now, if you consider dip needle, which is just uh, the needle of a compass, which is pivoted horizontally. It is pivoted horizontally, but it is pivoted in such a way that it can actually rotate in the vertical plane, and that vertical plane is coinciding with the magnetic meridian. So it orients itself so that its north pole finally points exactly in the direction of the Earth's total magnetic field. See, if you do this way, like if you just pivot this dip needle in such a way that it can rotate in a plane, vertical plane, which is exactly coinciding the plane of this magnetic meridian, then at the equilibrium position, the north pole of this magnetic needle, or sorry, this dip needle will orient in a direction similar, in a direction which is the direction of the total magnetic field of the Earth magnetism. So this is the way to find out the direction of the total magnetic field of the Earth. Okay, so now see, this is the total magnetic field which is directed in this way, and this total magnetic field is making an angle delta with the horizontal direction of the magnetic meridian. So now see, we can see another component. See here, okay, let me write this. See, at the magnetic equator, this dip needle will rest horizontally. That means what? The dip angle is 0. Dip angle will be 0 at the equator. You have to remember this. Dip angle will be 0 at the magnetic equator. And what will be the angle of dip at the pole? It will be 90 degree. Okay, because the needle will be perpendicular to the pole. Okay, perpendicular, or it will be orienting itself vertically at the poles. Hence, the angle of dip is 90 degree at the magnetic poles. So therefore, we can see that angle of dip lies between 0 degree and 90 degree at all places other than this pole and the equator. Equator it is 0, and at the pole it is 90 degree, and at all other places it has value in between 0 to 90. So this is actually about angle of dip. Now see, I just, okay, let me go to the next part. Okay, so third parameter is the horizontal magnetic horizontal component of magnetic field. I need this figure, so I'll just copy this figure to the next page. See here, this is the third component of the or third element of the magnetic earth magnetic field. So if I know the angle of dip at any position, and if I know this angle of dip, then what I can do, I can get the horizontal component of magnetic field. That is actually the magnetic field, the total. See, this is the total magnetic field which is making an angle a delta, which is angle of inclination, and that angle is made with the horizontal direction of the meridian plane. So BH will be actually total magnetic field into cos of delta. What will be the vertical component over there? Vertical component will be B sine delta. Okay, now if we know only cos delta, so if I know only this BH, so from here also we will be able to find out the total magnetic field. So component divided by cos of delta. So here also we can be able to find out the total. So if I know this I know the delta, I know the BH, so then I can get the magnitude of the total magnetic field. Now BV is this, so from here also we can get, see, I can just write BV, I can just take the ratio BV by BH, which is actually tan delta. Okay, so what will be this delta then? Delta will be tan inverse of BV by BH. Okay, so this is tan inverse of this. Okay, so if I know both these components, then also we'll be able to see vectorially, we can just find out, see, this magnitude of the total magnetic field will be obtained from BH square plus BV square. So this is another way to find out. Okay, so we can see that three elements or three parameters, essential parameters, are angle of declination, angle of inclination, which is delta, and the horizontal component of the magnetic field, BH. So these are three essential parameters determine the magnetic field of the earth at any place. Okay, now see, I know this delta is the angle of inclination. Now if suppose delta 1 and delta 2, there are two angle of dip when it is determined in two planes which are perpendicular to each other. Okay, in two planes which are perpendicular to each other. Okay, so this is another plane. Okay, so this is, sorry, so which are perpendicular to each other. If we find out two angle of inclination at two different planes which are perpendicular to each other, then the true angle of inclination will be inclination. True angle of inclination will be, see, I can actually draw like this. So these are suppose two planes. So if I get angle of inclination delta 1 with this and delta 2 with this, so the true inclination delta could be found out like this. See, cot square delta will be cot square delta 1 plus cot square delta 2. Okay, so this is how we can determine. Okay, now we may take up some examples. Okay, so let me just take you through one example. Suppose deep circle shows suppose a, a deep circle shows an apparent deep angle angle or angle of dip. I'm just writing in short, dip angle 60° at a place where the true dip angle is 45°. If the circle is rotated through, if the circle is rotated through 90°, what apparent dip will it show? So this is the question. See, as you know, we had already discussed this. If I have two planes, suppose this is plane 1, this is plane 2, and if this is some delta 1, this is delta 2, so this will be total, this will be I'm sorry, this is okay. So this is actually, this is the direction. Okay, anyway, so what we had already discussed, we know we have a formula, right? So we have a formula, so we know d delta 1, so here it is, we know delta 1 is 60 and the delta is 45. So we know from this formula we will be able to directly find out cot square 60 plus cot square delta 2. So this we have to find out. This is 1 minus cot square 60. So 60 cot 60 means 1 by root 3. I can just write 1 by root 3 square So that will be equal to cot square delta 2. So this actually will give you cot square delta 2 is equal to 2 by 3. Okay, 2 by 3. Or cot delta 2 will be square root of this, and if you take the inverse of this, so delta 2 will be nearly 51 degree. It will be nearly 51 degree. Okay, so we can use of this formula as we have learned. Cot square delta is equal to cot square delta 1 plus cot square delta 2. So this formula we can use to find out the another apparent angle at the perpendicular plane. Because this circle was rotated through 90 degree, so it is in the another plane it is. Okay, so earlier it was suppose here, now it is now here. So we have to find out the apparent angle in this plane. Okay, so we'll stop it here with this. In the next class we'll be learning about various type of magnetic materials and their applications. Okay, so thank you for your patience. Bye for today.